Hi everyone, this is Happy. Welcome to StepUpTech Academy. Today we're going to be doing a deep dive on the PostgreSQL architecture. So let's dive right into it. So imagine that you go to Amazon.com, right, and you want to buy a shoe. You want to update your address. Let's just say you want to update your address. For some reason you've moved and you want to update your address. So what are you going to do? You're going to go to your laptop. Okay, you're going to go to your laptop and then you type www.google.com, right? And then when you type www.google.com, you're going to hit the web servers for Google. And then on Google, you're going to type www.amazon.com, right? So www.amazon.com is what we call the presentation tier. The presentation tier is simply just the user interface. That user interface where you interact, right? You go to Amazon.com, you see like the shows, different things. So that's the user interface, and it acts like a communication layer between the application and the back end. It acts as the communication layer between the application and the back end. And this is where you perform your user action, right? When you want to update an address, you want to purchase an item, you want to send money to someone. So it could, if you're doing it on your banking application like Bank of America, you're going to meet the presentation tier. That is what you're going to meet. And from there, ignore this step 9 and step 10. So we're going to get back to it. But we're moving like this. Here, you go to google.com and then you get to the presentation tier, and then from the presentation tier, your request, let's say for example you want to purchase an item, right? That request will go to the next level, the next tier, which is the application tier. So at the application tier, what's the application tier? The application tier is the logic tier or the middle tier. That is simply the heart of your application. So the code for your company will reside, the code for the Amazon company will reside in the application tier. This application tier is not exposed to the internet. It is an internal, we have application servers, right? Here we have web servers. These web servers are exposed to the internet, but application servers are not, because it contains the source code, the code that was used to build that application. If anyone lays his or her fingers on it, that code is gone, that company is gone, because they'll just replicate that company. So this application tier is highly secure. And what do we have in the application tier? We have something called the business logic, the logic of the application. Think about Prime and Amazon.com. They all function differently. Prime is for videos. Amazon is a platform for buyers and sellers to meet, right? So that's the logic. The logic is for a buyer and a seller to meet and then perform a transaction, right? But on Prime, you go there, you buy a movie, you watch. So the logic is different. The logic for the application, the application logic is stored in the application tier. And one of the functions of that logic is to convert your user action. Whatever you try to do in a presentation tier is to convert that user action into an actionable item or into a language that the database is going to understand. And that language here is called the structured query language. The structured query language. That is the language that the database understands. And once that is done, the request is then fired to the data tier. So in the data tier, we're talking about the database servers. And the data tier is what is of interest to us. What exactly happens when we get to the data tier? So in the data tier, the first step when that request comes into the data tier is going to meet a background process, right? We said that the database is divided into 3 main components, right? We said the database is divided into 3 main components. So it's divided into memory structures, process structures, and storage structures. So we're going to look at background processes, we're going to look at storage components and memory components. Okay, so this postmaster process is a background process, and this postmaster is the parent, is the master. It controls all the other processes. So it's the parent to all the background processes, and one of its main functions is to assign workers, right? Is to assign workers to the user or the client. Remember the request here? The request here is to update an address, right? So the postmaster will find a dedicated worker. Think about a chef in a restaurant. The chef is just standing there making sure that everything is working fine, but he is not doing the heavy lifting. The cooks are doing the heavy lifting, right? The chef is just there, to manage everything. The manager is just there to manage everything. That's what the postmaster does. He receives the request, just like a customer who comes to a restaurant. The chef will receive that customer and then assign a steward or a cook for that person, right? It's the same thing with the postmaster. The postmaster will sit and wait for incoming requests, and when that request comes in, it's going to assign, it will create a back-end process called the Postgres process or the back-end process to handle that request. And what's the request? The request is to update the address. And so this back-end process will be responsible for that. The back-end process will be responsible for updating that address. So what is another function of the postmaster? When you start up your cluster, when you start up your database cluster, the first process that comes up is the postmaster process. When that postmaster process comes up, what it's going to do is it's going to start all the background processes, all the other background processes. We're going to talk about that, but it starts all the background processes when the cluster is started, and then it allocates the memory that will be used. Remember that we said the cluster is made up of process structures, memory structures, and storage structures. So it's going to allocate the memory that the cluster is going to use. It will grab some memory from the operating system and then allocate it to the cluster for it to use it for database operations. So when the request comes in, the postmaster will quickly create a dedicated worker process called the back-end process that will handle this client request end to end. And one thing you need to understand about this back-end process is that it handles all the queries issued by that client. It's going to handle all the requests issued by that client, right? And you need to understand that it's just one back-end process per client, right? One back-end process. You don't want to have one back-end process working for multiple clients, right? The back-end process will not be efficient. So the postmaster dedicates each back-end process for each client. And notice that the back-end process only exists when the request comes in. When the request comes in, the back-end process is created. It doesn't stay forever, right? It doesn't stay forever. So it gets created only when a request comes in. The postmaster will create it when a request comes in so that it can work for that client. So for step 3, when the back-end process is created, that back-end process will now get into the memory, right? It's going to get into the shared buffer. One of the main components of the memory is called the shared buffer, right? The shared buffer is a component in memory that will store copies of data. It will store copies of your data. So when the back-end process gets into the memory, what is it looking for? Remember that memory is fast. So we want to make sure that the database tries to keep data in memory for as long as possible. So when the back-end process gets into the shared buffer, it's trying to find out if someone has done something like that before. If someone has copied that data that it needs to work on. If someone has copied that data to memory before. So it will check the cache. So it's going to check the cache. If no one, you see step 3, is going to check if the data it's looking for is cached in memory. If the data is, if that data is in memory, we'll call that a cache hit. If it's in memory, it's called a cache hit. But if it's not in memory, it's called a cache miss. It means that that data is not there, right? And we want to modify our data in memory because it's faster in memory. So what are we going to do? The back-end process will come and make a copy of that data. It will make a copy of the block, right? You see the back-end process in step 4, making a copy and bringing it to the memory. When it brings it to the memory, it's going to occupy what we call a free buffer, okay? I know it's pointing to a dirty buffer. It's because of what happens after, right? But when it brings this block to memory, it becomes a buffer, and it comes in here and occupies a buffer. As you can see here, there are three types of buffers. We have the free buffer, we have the busy buffer, and we have the dirty buffer, right? So when the data is not in memory, it goes to disk, makes a copy of that block, brings it in memory, becomes a buffer, and then it gets into what we call a free buffer, right? A free buffer is a buffer that has no data, it has nothing going on, right? So you go in there and make use of it. Immediately that data is copied into the free buffer, that buffer becomes a busy buffer, right? So busy means that, hey, right now we are performing that transaction. Remember that the request comes from the application tier to the data tier in the form of a request. So that request has to be executed. That request is executed in this busy buffer. So when it's busy, no one can bring another copy of that data, another copy of data from data file to memory and put it in that busy buffer. No, when it's busy, it's busy. From what busy, you understand that busy means do not disturb, right? I'm busy. So it's going to perform that transaction. It's going to perform that update. Update address, set the new address to 1234 Canton Road, where the ID is 1, commit. So this is where the transaction will take place, in the busy buffer. Once that transaction is done, once the user says update the address, right? Complete this thing. This busy buffer will become what we call a dirty buffer. So a dirty buffer is a buffer that contains committed transactions that have been completed already. So when the transaction is done, it changes from busy to dirty, from busy buffer to a dirty buffer. Are we together? So it converts it from a busy buffer to a dirty buffer. So the transition is free to busy and then to dirty. That is the end state of this buffer. It becomes a dirty buffer once the transaction is done. Now, the transaction is complete. I'm sure you're thinking the user needs to receive confirmation that the address has been updated, right? But that doesn't work that way. You can see in step 5, the block was copied. It was copied into a free buffer. That free buffer became a busy buffer, and the data modification happened, and the transaction got committed. And after it got committed, it became a dirty buffer. Now, what happens when this buffer becomes a dirty buffer? In a normal scenario, this dirty buffer needs, once it's committed, the customer needs to receive a message or a confirmation that the address has been updated. But something needs to happen before that. Notice that this is the memory. The memory is volatile. Right now, we have performed changes, we have finished the changes, everything is done, everything is committed, it is now in the dirty buffer. But there is a problem. When we copy that data from the data file to the memory, and then we've modified this data. Imagine that address was 457 Canton Road. Now we're changing it to 1243 Canton Road. The data on disk is now outdated compared to the data in memory, because the updated data is now in memory, right? So, and we know that memory is volatile. What if this memory crashes? What if the Postgres crashes abruptly? What if the server goes down? This data in memory will vanish. This data in memory will go away. And if it goes away, that's a big problem, right? Because imagine that the user has already updated his address, and then this memory crashes immediately when the data has not yet been sent to disk. What will happen is that you need to go and tell the user that, hey, can you please put in that data one more time? And the user will be very, very angry, right? The user might probably go to another platform. So how can we prevent that? Since this memory is volatile, we have another memory component called the wall buffer. What is the function of the wall buffer? The wall buffer is there to store changes, all the changes that occurred, all the changes that happened here in this shared buffer. Since we need to keep that data on disk, we need to store that data in the wall buffer and eventually down to disk. But why does this wall buffer come into play? It comes into play because we have a certain background process called the background writer, and the function of this background writer is to write the dirty buffers. Note that it writes dirty buffers, not busy buffer. Busy, transaction is still going on. Free, there's nothing in there. Once it's done, it becomes a dirty buffer. This is the one that contains the committed data or the completed transaction. Normally, the background writer needs to write this dirty buffer to the disk, but it is lazy. because this dirty buffer, it contains a lot of data, right? So if this background writer is writing all the time, the performance of the system will get degraded. So it writes periodically, it doesn't write all the time. So but we need to find a way to store the changes that occurred in this dirty buffer somewhere. Since this background writer is lazy to write everything to disk, we need to find a way to write ahead of this background writer. And that is why we have what we call the war buffer. So the war buffer will receive the changes that were done by the dirty buffer, and then another background process called the war writer, we call it the fast writer, because immediately the transaction is committed, that war writer will immediately write all those changes to the war files, right? So you see step 6, the back-end process will copy those changes from the shared buffer to the war buffer and then to the war files before the user will receive confirmation. We are just trying to avoid a situation where we need to go back to the user and tell the user that, hey, the memory crashed, we lost all your changes, you have to put in that data again. The customer will be very furious. So what we need to do is that we have to write ahead of this background writer that was supposed to do his job but is not doing it in a timely manner. We need to write ahead of this background writer, and that's why we call it war, write ahead log. So this background writer will write immediately a transaction is committed. So the war writer will copy the changes immediately from the war buffers to the war files on disk. Once that data reaches on disk, once that data lands in this war file on disk, now we can say that we are safe, right? If this memory crashes, it doesn't really matter because those changes are in the war files, and we can always roll forward all those changes into the data files if this instance crashes. So note the process here. The back-end process gets into the memory, it tries to find data. If it cannot find it, it goes to the disk, makes a copy of that block and brings it into a free buffer. And then once it brings it into the free buffer, it becomes a busy buffer. Once it's done modifying it in the busy buffer, that buffer becomes a dirty buffer, right? It's the same buffer. I'm just explaining the transition. It's the same buffer. It changes from free to busy and then to dirty, right? But since the background writer does not write very fast, and we need to, the back-end process will copy those changes. What's the change? The change is 1243 Canton Road. That's the new address, right? It will copy that change to the war buffer, and a very fast writer will copy those committed changes from the war buffers to the war files on disk. So it needs to write very fast ahead so that the user can quickly receive the confirmation, right? So you can see step 8 is going to write everything on disk. And once those changes are on disk, what will happen is that the results will get returned to the application tier, right? Usually the database stores data in the form of tables, rows and columns. So it might return that data to the application tier in the form of rows and columns. And since the application tier has the business logic to convert the results from the data tier into a format that the application will understand, the application logic will convert those results into a viewable format for the user. And that is when the user in step 10 now sees that the address was updated. So one thing I want you to note here is that this user will only see that the address was updated once the war writer has written to the war files. Why? Because we don't want that the memory crashes and we are asking the user to repeat his changes. So once those changes are in the war files on disk, then the user will receive confirmation that the address was updated. Now, if something now happens to this memory, we're not going to bother, right? Because we have our war files that we can use to recover our system. We have the war files to replay all those changes that occurred in memory. Everything is here. That's why we call the war writer a fast writer, because it writes ahead of the background writer. So once the user receives confirmation, it ends the life cycle of that statement, of that request. But other things need to happen in this system, right? The fact that the background writer is lazy and does not write to the disk on time doesn't mean that it will never write. Something needs to force this background writer to write. So there's a background process called the checkpoint process, and that checkpoint process is responsible for forcing. It will force the background writer to write to the disk. right? It will force this background writer to write to disk. So during the checkpoint, the background writer will flush all those dirty buffers containing all those changes. It will synchronize it with the data on disk, because right now in memory has more up-to-date data than the disk. So after some time, we want to synchronize what is in memory with what is on the disk. So background writer will be responsible for flushing the dirty buffers, not busy buffers, dirty buffers. Dirty buffers contain committed transactions. So the background writer will flush the dirty buffers from the memory to the disk. Once it's on disk, guess what? You can see that dirty buffer here, right? That is the background writer that has written that file, that buffer. So you go into the page in the data file, and once that is done, guess what? These WAL files are no longer required. Why? They are no longer required because this WAL writer wrote ahead of the background writer, because background writer could not write those changes, right? So we use a fast writer to write it ahead of the background writer. Since it's lazy, it's slow to write, so it writes ahead. It writes those changes. The WAL writer wrote those changes ahead of the background writer. But now, since the background writer has written all those changes, now we kind of have like a duplicate, right? We have those changes here, and we also have those changes here. The end goal is to have your data persisted to the data files. But since we now have those data in the data file, we now, and also in the WAL file, it's kind of redundant, right? So since the data has already been copied to the disk, to the data file by the background writer, we don't need this data anymore, because this location is very busy. You see, the WAL writer is very fast, so it writes all the time. It keeps on writing. So we want to be cognizant of the space in this location, in this folder. So once the dirty buffers have been written to the data files, have been copied to the disk by the background writer, the changes in these WAL files are no longer needed. Now, what happens next depends on if archiving is enabled. If we enable archiving, a background process called the archiver process will copy all those changes that were in the WAL files to an offline location called the archive WAL files. You copy all those WAL files to the archive WAL files. Which background process does that? The archiver process. If archiving is not enabled, you discover that these WAL files here will get recycled, because we don't want to have redundant stuff, right? Those changes are already here. We don't need these changes here anymore. We are copying to the archive WAL location because we might need, even though we don't need it right now, we might need these WAL files in the future. If this data file gets corrupted, you can restore your backup and then you apply all these WAL files to reach a consistent state. So these WAL files are still very important. In fact, the WAL file is one of the most important components in this architecture, because if you lose your WAL files when that background writer has not yet written, then, or if you lose your WAL file or all your files, you'll be in trouble, right? So if archiving is not enabled, it's going to recycle it immediately. But if archiving is enabled, the archiver process will copy those WAL files from here to the archived WAL files. And you have to be very careful with the WAL files. You never use rm-rf to delete your WAL files, even if that location is getting full. You don't use rm-rf. And the condition for recycling this WAL file is that the background writer has flushed the changes to disk. If those changes are not on disk, these WAL files will still contain those changes forever and ever, right? Until background writer flushes everything to disk. Once it flushes everything to disk, then we don't need this anymore, because our goal has we've satisfied our goal, right? We've met our goal, so we can remove this. So the condition for recycling our WAL file is that the background writer has written those dirty buffers to the disk. Now, there are other background processes like the auto vacuum process. You know, as you're performing updates, deletes in the system, those updates are generating like garbage in the system. And after some time, we need to perform an auto vacuum. The auto vacuum comes in to clean up that garbage in your database cluster. So that's the function of the auto vacuum process. The next process is the logger process. This system will not always be running smoothly. You will have some errors once in a while. And when you have an error, the logger process is responsible for copying the errors from your cluster to the error log file. And then you have another process called the logical replication launcher, and that is used to set up logical replication. And then you have the stat collector process that is used to collect statistics. Thank you very much for watching. That is it.